EUSMI is a network of European institutions providing access to cutting-edge research infrastructures. Further, they are developing experimental techniques to allow an even deeper insight into the functioning of soft matter materials. A collaboration between three partners exemplifies how joint research efforts lead to new options, which also benefit researchers outside the network.
My name is Luis Liv Marzang. I'm the Scientific Director of the Center for Cooperative Research in Biomaterials, CIC Biomagune, located in the city of San Sebastián in Spain. We are members of the EUSMI Consortium, which is a group of laboratories in Europe with expertise in soft matter research, and we are mainly specialized in the fabrication of so-called nanomaterials, and this is the expertise that we offer to the network. So nanomaterials are very tiny pieces of materials, typically of a size of a millionth of a millimeter, and because of that size they have very special properties. We mainly work with gold and other metals because gold in the nanoscale has very special properties, in particular regarding to the interaction with light. So when light is coming on the nanoparticles, it can be absorbed in different colors and it can be either reflected or released into heat. So we apply part of these properties for detection of very small amounts of molecules. In our case, because we want to work on biomedical applications, we detect so-called biomarkers of diseases of different kinds, for example, of cancer. The same nanoparticles can also be applied for therapy to kill, for example, tumors, because when the nanoparticles are located in contact with the tumor, they can be irradiated with light and the released heat will be used for killing the cells. Now, for these properties, the nanoparticles have to retain their original morphology. Most of these applications profit from morphologies containing like sharp tips, what we call nanostars, and these particles can also be unstable under different conditions, for example at high temperatures. So in order to understand the possibilities of using these particles for these applications, we need very detailed morphologies on how high temperatures these sharp particles will stand before they reshape into spheres. For this we have access to the electron microscopy laboratory at the University of Antwerp, the EMAT lab, which is led by Professor Sarabals, one of the best labs in the world for characterization of nanomaterials.
Gold nanostars are prepared by chemical reduction in aqueous solution. Spherical nanoparticle seeds display a red color. Upon addition of ascorbic acid, the tips grow and the color becomes blue, with a characteristic absorption band in the near-infrared as measured by optical spectroscopy. For characterization in an electron microscope, a tiny drop of the solution containing nanostars is dried on top of a special copper grid.
My name is Sarah Bals and I am the spokesperson of EMAT, which is the electron microscopy facility here at the University of Antwerp in Belgium. Our goal is to investigate soft materials and nanomaterials with resolutions up to the atomic scale. Within EUSMI, we are developing novel three-dimensional characterization techniques for such materials. We do so by using electron tomography, which is a technique where we collect a large number of projection images of the same object of interest, and then we use a computer to obtain a three-dimensional visualization of the structure. We have used electron tomography quite a lot in the collaboration between EMAT and the group of Professor Luis Liv Marzang in San Sebastián.
I'm Dr. Wiebke Albrecht and I'm a postdoc at EMAT, mainly involved in in situ heating studies. Anisotropic metal nanoparticles are unfortunately very unstable and they start to reshape at temperatures hundreds of degrees below their bulk melting temperature. To understand this, many studies have been conducted so far, and it has been related to the curvature of the nanoparticle. The sharper the tips, the more it deforms. However, these studies have been mainly done by indirect means, like optical techniques or ensemble average techniques. So we thought we can do that in the microscope, by heating nanoparticles in situ and following the same nanoparticle. However, because these metal nanoparticles that we are mainly interested in are highly anisotropic and highly asymmetric, we need to do tomography. 2D projection images are simply not enough. So we needed a new holder that combined heating and electron tomography, and this is why we went to dense solutions.
Hi, my name is Hugo Perez. I'm the Chief Technology Officer here at Dense Solutions. Dense Solutions is a company that started about 7 years ago as a spin-off company from the University of TU Delft here in the Netherlands. It's a company that throughout all these years we've been focusing on trying to develop new technologies and bring an added value to those users within the electron microscopy community. To do this, and in order to give that added value that I was referring to, we've been basically focusing on different technological domains like hardware, software, electronics, and MEMS technology, which at the end of the day is what we consider is our core competence. So by putting all these elements together, we bring to the user a comprehensive system capable of providing the capabilities to manipulate the molecular structure of their sample as a function of different stimuli that we can offer via our different product portfolios. Particularly with the people from EUSMI and the collaborators that we have there, this is the system that we have used. It's a system that once you introduce in the TM, it allows for alpha tilting with plus minus 70 degrees of freedom. And it's a system that together with these MEMS devices that we can see here, we create basically a closed loop feedback system so that the customer can have the means to have or to benefit from very high temperature stability, very high temperature accuracy, and therefore make sure that as they're tilting and as they're increasing their temperature, they would be able to do all the reconstruction of the 3D image in a very controlled manner. So we hope that with this technology and this collaboration that is in place within EUSMI, we can really reach very high impact publications and of course bring an added value to the community that is already working on this.
Now with the holder from Dense Solutions, we have all the tools needed to perform our experiments. However, we soon realized that we still have one major challenge to overcome. And this is simply because now a typical experiment would be to increase the temperature, and after every temperature step or time step we would acquire a tomography series. However, in order to capture fast dynamic processes, we need to be able to do this in a fast way. But a typical tomography experiment takes about 1 hour, and this is simply because we tilt the holder, we focus the particle, we acquire an image, and we do that about every 2 to 3 degrees for a large angle range. So we developed a novel methodology in which we continuously rotate the holder and acquire a movie, which allows us to get the same 3D information but about 10 times faster. In this way, we can now really follow in situ dynamic processes with a good time resolution and also enable high throughput experiments. With the new methodology, we now went ahead and studied the gold nanostars at different temperatures. We chose 200, 300 and 400 degrees, and after every 30 seconds of heating, we performed a tomography experiment over the course of 20 minutes. In this way, we could directly visualize how the particles change. For the nanostars, it was then obvious that indeed atoms from areas of high curvature, such as the tips, depicted in red, move to areas of low curvature, which are now here depicted in green. We could quantify that by just measuring how much volume was redistributed, and moreover, because we have the full 3D datasets, we could also analyze the curvature, which is important in determining the optical properties. So in order to couple the optical properties to the change of the nanoparticles, we then took our 3D reconstructions and we put them in simulations. And in this way we could directly show that the decrease in curvature leads to a decrease in their optical activities.
What is really nice about this project is that it is a true joint research activity between 3 EUSMI partners: DenSolutions, CIC Biomagune and EMAT. Moreover, our work has attracted the attention of international research groups, and consequently they have applied for transnational access. This has resulted in 2 more papers, one with the group of Professor Sarah Skrabalak from Indiana University, and another one with the group of Professor Alfons van Bladeren with Utrecht University in the Netherlands. So if you are interested in applying for transnational access, do check the EUSMI website where all information can be found, and we look forward to collaborating with you in the future. So, Sarah, we are here in Paris for a conference about nanomaterials and nanotechnology. And we both gave presentations, and in both of our presentations we mentioned our collaboration and the recent results that we obtained. But I would like to go back to the beginning and ask you what it was that attracted you about the work that we have been doing in the EUSMI framework.
Oh, yes. So actually, it all started when I was on sabbatical in Spain, working in Luis Marzan's laboratory at Biomagune, who you have a long-standing collaboration with. He was sharing some of the beautiful results that you have obtained together, and I started to imagine just how your techniques could be applied to our material system.
So yeah, I'm very happy about the way that this collaboration turned out, and it was a pleasure investigating your materials. You are also an editor at Nanoscale, so you likely have a very broad perspective on what is going on in the field. Could you comment on why you think it's important to investigate these materials in such detail, because it is a very local technique?
Yeah, of course. Well, I think it really comes down to seeing is believing. There are so many questions that people have about nanoscale materials, and oftentimes we try to draw conclusions without a whole lot of direct evidence for the observations that we are making. And so using these advanced microscopy techniques just actually lets us see our particles and how they change under different stimuli, and if there are different types of defects or compositional variations that might account for some of the properties that they're displaying that isn't obvious from a bulk measurement.
I see. So right now we have investigated gold palladium octapods, and we looked into their thermal stability. Yeah. Do you see any follow-up studies where we could collaborate?
Definitely. Well, first, that study was just so beautiful to be able to see how they reshape when they're being heated, and what locations are the first places or first sites to deform, and how composition can play a role in the stability that the particles play. And now I'm really fascinated by the role of defects, and how defects can contribute to the stability or instability of nanoparticles when being heated or in response to some other type of stimuli.
Right, that's very good to hear, because within the EUSMI project it's very important for us to understand from the people that apply for transnational access what kind of techniques we need to develop in the future. So that is really good feedback. So thank you very much for taking the time to explain to us how EUSMI has been important in your research, and I hope you have a good trip back home, and that the next time we meet somewhere around the world, that we have many more common publications following from our collaboration.
Yeah, it's been absolutely wonderful working with you and your team. So I look forward to future collaborations
Likewise,
as well.
Yes.